Okay, so welcome to this knowledge sharing session promoted by Altice Labs devoted to 5G. My name is Francisco Fontes, and today I will provide you with information on requirements, technologies, and impacts related to the emerging fifth generation of wireless terrestrial communication systems. You have my email on the screen, which you can later use to put me questions related with this presentation. I will try to answer all of them with the knowledge I have on the topic. Oh. Okay, just a moment. Can you see my? Okay. Okay, going to the next slide. So this is the agenda for the session, for which we'll be together for about the next 25 minutes, in which I tried to aggregate somewhat topics on 5G, trying to cover as much as possible of the most important aspects of the technology. We'll start by understanding what is expected from 5G. In fact, the hype around 5G is big and growing, promising a whole new bunch of nice things, in part fostered by the industry trying to sell their products, resulting from many years of research and prototyping investments. So 5G is no exception on this, and so the industry and also the operators are pushing and making some announcements on 5G, trying to push the technology and creating lots of expectations regarding to this. On these slides, and as we can say, and as the 5G name denotes, it is the fifth generation of mobile wireless communications. The history of the terrestrial wireless communications is not so long. It started in the 18s with its first generation. At that time, the objective for the network was to allow people to make phone calls while moving. That was not possible, only the fixed network was available. At that time, this was supported by big, heavy terminals, and voice was analog. So the first worry people had was to allow people to talk while moving. The second generation arrived at the beginning of the 90s, provided digital, not yet IP voice for better quality via GSM in Europe. In meanwhile, terminals became smaller and batteries last longer. Even if data based on IP was later introduced, it was narrowband via GPRS and later edge systems. The third generation arrived with the 21st century, providing what was called mobile broadband. Voice is still digital and still non-IP, being circuit switched. Data still is, or as with previous generation, is IP, packet switched, with CG representing both circuit switched and packet switched domains. Around 8 years ago, the fourth and last generation appeared. Bit rates increased a lot, paving the way for the mobile internet. Besides the higher bandwidth, this technology does not have the circuit switched component. Thus, all communication must be IP-based. For voice, solutions were developed going from VoLTE, which is voice over IP with guarantees, to circuit switch fallback, which switches the terminal radio to 3G while the voice call is taking place. By coincidence or not, these successive generations appeared approximately at each decade. Continuing that pattern, 5G is not expected to have the first commercial deployments before 2020, besides some recent marketing announcements. In most cases, those correspond to pre-5G or 5G LTE Pro, not for sure 5G. And these announcements happen because 5G is attracting a huge expectation, partially justified by the big improvements it is expected to present. In the bottom of the slide, we can see the terminal's evolution. From big with limited autonomy, we evolved to smaller, long-lasting batteries. Recently, we sort of returned to bigger, high-energy consuming terminals as a result of the new utilization models requiring bigger screens and being always connected and making traffic. 5G, for sure, will foster this type of utilization. From this slide, we should retain three main ideas. That so far, every decade, a new generation appeared. Focus so far in this evolution path has been in achieving higher bit rates and higher mobility, and terminals have become bigger and high energy consumers, what we had at the beginning of with 1G. From previous slide, we could see that evolution path until the fourth generation provided progressively higher mobile bandwidth, guaranteeing faster internet accesses. However, 5G is expected to go beyond that utilization. Here we can see three 5G definitions coming from three different relevant organizations, namely ITUR, NGMN, and 5G PPP. The first is Standardization Organization, while the third shall represent European view on 5G. What is common in all the definition is the expected impact 5G will have in the society and the global economy. Expected usage scenarios, as we'll see in the next slides, will go well beyond internet access and mobile broadband. 5G is expected to enable a connected society, bringing together people, things, transportation, cities, industries, and more. Thus, 5G has the potential to become, as IHA says, a general-purpose technology to the expected impacts and the role it may have in the future, being comparable to the impact first steam power, then electricity, and lastly robots had. Thus, we may say that all the hype created around 5G is justified if, at last, the technology succeeds fulfilling the established requirements. We will see now the 5G expected use cases and 5G requirements. This already mentioned 5G expectation is reflected in the large number of documents referring to 5G use cases and application scenarios. From those use cases and usage scenarios, 5G requirements have been in most cases derived. In this slide, which we will not analyze in detail, I just put some examples of the work done by some entities, namely NGMN and 3GPP. NGMN presents on its 5G white paper a number of use cases 5G is supposed to enable. These go from pervasive video, what requires a sustainable bandwidth everywhere, to EL scenarios where low latency and reliable communications are mandatory. On the right side, there is a figure extracted from 3GPP Smarter Work. Use cases are here organized along several vectors, which we'll see next. From these, potential service and operational requirements were extracted and feed 3GPP standards being developed. These figures in this slide, taken from ITUR, show the identified usage scenarios and requirement set organized along a set of 8 key capabilities. The usage scenarios are organized in 3 main groups in line with the 3GPP Smarter Work. First, we have enhanced mobile broadband, being this focus in obtaining high bit rates while moving. The second group is massive mobile type communications, focusing in efficiently support IoT devices. And lastly, in the third vector, we have ultra-reliable and low-latency communications for communication requiring, as the name states, reliability and low latency. On the key capabilities enhancement side, on the right, we can see the comparison between 4G and 5G. 4G is the internal line, while 5G is the external circle. In the figure, we identified the factor by which its capability is demanded to improve. In fact, some expected improvements are really demanding and require significant technological evolutions as well as strong investments from the operators that will deploy the technology. As examples on these key capabilities, we can see that latency shall go to values around a few milliseconds, while users shall perceive as a sustainable bandwidth in the order of several hundred megabits per second. Besides the work done by TUR on the identification of the key capabilities, 3GPP, the main entity behind 5G standardization, also extracted service requirements for the 5G system. This is documented on 3GPP Technical Specification 22261. We will not go through all the items identified here. The document is public and you can read them freely. From all the enumerated characteristics, I just want to highlight some aspects. First, the network slicing. Second, multiple access technology support. Broadcast, multicast support. Support for minimal service requests. Long-range coverage and high accuracy positioning. This shows the wide range of applicability targets envisioned by 3GPP for the 5G systems. That may well be the biggest challenge, so to support all these capabilities and these requirements on the single system. So what in fact is 5G? This slide tries to summarize it. As we already saw, it is a next generation communications network. And here I omit mobile and add the term services going well above the network layer. In fact, as stated in next point, 5G plans to go beyond the wireless, also integrating the wired media. and it shall enable a new generation of services that will take advantage of this new technology. As referred before, it shall present a significant improvement over previous technologies, what shall be measured by a number of well-identified KPIs as stated in the previous figure from ITUR. For this to be possible, a new radio interface and a new system architecture are required. Thus, in fact, 5G can be described focusing on that new architecture and new 6GP radio interface, as we will do later. Since 5G is expected to provide its service to a large spectrum of use cases, it must be very flexible and very reliable. This being directly dependent on the way the technology is defined as dependencies on the complementary technologies used to make 5G reality. Here we can refer to SDN and NFV, which shall play an important role in 5G deployment, management, and operation. Finally, standardization and industry are expecting and pushing 5G to be ready for the first commercial deployments to take place in 2020, even if some pre-5G and trials will be run before. This figure summarizes what we understand as being the 5G system. Besides the enabled application scenarios and the supporting technologies, it is also important to analyze 5G from other perspectives. Here we can see some numbers related to 5G expected impacts regarding number of subscription and other economical indicators. The impact 5G will have in the economy is significant, as we can extract from these statements. Here we can see that some consultancy companies expect regarding jobs to be created and contribution to GDP. In the table in the right, please pay attention to the columns names EMBB, MIOT, and MCS. These will appear in the next slides with a different name. We can see that 5G is expected to have an heavy impact in almost all industries, as it is expected to create lots of jobs and to contribute heavily to the global world economy. In the next coming year, we will assist to a number of events which will be used for 5G demonstration for both the technology and the supported use cases. We will start next year with the Winter Olympic Games in South Korea. Most probably, these will be based in pre-5G components since standardization will be not ready at this time. Then we'll have the UEFA Euro 2020, the first big event for Europe to show its advances in 5G. Next, there will be the Summer Olympics in Japan. And to close, we'll have the Winter Olympics Games in China in 2022, at that time with full 5G standards in place. Coincidence or not, all the 3 Olympics Games take place in Asia. Then we'll have this European commitment, which is aligned with the Euro event. So in 2020, besides the UEFA Euro Championship, Europe is also committing to have in each of the European state members at least one city with 5G commercial service launched. So we can say that interesting years are coming for us all to contribute and see what can be done with 5G. Before going into more technical content, one last slide with a figure coming from Ericsson and illustrating the expected evolution in terms of number of subscriptions for the various technologies or generations. We can see here that in the near future, the expected growth in mobile network subscription will be supported by 4G, while 2G will reduce significantly and 3G is not expected to grow. 5G will start appearing in 2020 according to all expectations and based in the emerging 3GPP standards. Now we go for the 5G standardization work that supports all the 5G developments. 5G standardization, as with previous generations, follows the calendar and the requirements set by ITUR. For the 5G specific case, IMT 2020 defines the main goals for 5G as IMT Advanced set them for 4G. In this ITU figure, we can see the expectations for 5G to start deployment in 2020, after about 5 years of development. It can also be seen from the same figure, the acceleration in development and deployment of the successive wireless generations. 3G or IMT 2000 took 15 years to be deployed, while 4G or IMT Advanced took 9 years. 5G or IMT 2020 arriving in 2020 will have taken 5 years to be his vision defined, to have the standards developed and to start products being developed for taking his deployment in commercial fields being possible. While IT is setting the calendar objectives, 3GPP is the main organization working on 5G standardization. 3GPP standards are issued by releases. The first 5G release will be Release 15, partially covering IMT 20T KPIs, focusing in some higher priority aspects as set by the industry. Focus for Release 15 will be on enhancing mobile broadband. This release, to be finished by middle 2018, is expected to go into production in middle 2020, considering the time required for the industry to develop and deploy products based on the produced standards. Then Release 16 will provide full answer to IMT 2020 requirements and will go into production in the second half of 2021, 1 year later. Of course, it may be expected the time between standards being ready and products going to market to be reduced due to all the pressure and expectation put in 5G. These Release 15 and 16 CB standards will be taken as IMT 2020 specifications. We'll go deep into technical details of 5G, starting by the 5G system architecture. In this, we will present the main general concepts upon which 5G system architecture is developed. This is stated in 3GPP Technical Specification 23.501. It starts by stating that the clear separation between user and control planes shall exist. This reflects a clear strategy to adopt SDN principles with all the advantages such architecture brings. It allows independent scalability, evolution, and deployments, for instance, allowing more centralized or distributed deployments of 5G. Second point refers to modularization and slicing. As you will see next, slicing is an important aspect of the end-to-end 5G system. The concept is introduced as the answer to achieve flexibility and be able to answer simultaneously and by the same physical infrastructure to so many different requirements as the ones presented by NAS mobile broadband and ultra-reliable and low-latency communication. And in order to do it in a flexible and efficient way, 5G functional blocks shall present the right level of modularity to instantiate the appropriate functions on each of the slices. Third, introduce the adoption services concept as the basis for interactions between architecture elements. This reflects an approximation to software development practices. Fourth, mentions direct interaction, which will be based on a sort of communication bus, allowing components to directly request service from others, even if intermediate components similar to diameter routing agents are allowed. Fifth, 5G core network will be access network agnostic, based on a common access core interface. Thus, 5G core will be a converged one, allowing 3GPP and non-3GPP access types, wireless and wired. 6, for the previous to be possible, a unified authentication framework is required. 7th, and in order to guarantee the required flexibility, for instance, to scale and relocate components, computation and state must be decoupled. 8th, capability exposure allows the 5G system to interact with external entities, for instance, at service layer, providing access to its inner operational information and status. 9th, in order to support low latency services and access to local data networks, user plane functions shall be able to be deployed centrally or close to the access network. And 10th, lastly, and as already supported by 5G, when roaming, user traffic may be routed via its home network or be inserted locally at its current location. Based on the presented general concepts and undefined requirements, the following architectures is being standardized. The figure is taken from 3GPP Technical Standard 23.501. As stated, its objective is to be agnostic relatively to the access network time, behaving as a common core for different access technologies, 3GPP and non-3GPP, wireless and wired. For that, you can see the figure at the left bottom corner where you can see the same core being shared by different access technologies, where these N1 and N2 interfaces will play an important role achieving this objective. This architecture inherits many concepts from 4G being an evolution of those, even though it progresses in the details, incorporating the general concepts presented before. We can see the clear separation between the user plane and the control plane. The control plane is very modular with these main 7 functional blocks. This modularity allows a flexible deployment using, for instance, slicing. And for that, you can see the figure at the right bottom corner. Communication between components can be done directly, even if in practice, components only interface with a subset of the others. These components will be stateless, resorting to external data storage functional blocks not represented. In a slice deployment, some of the depicted components will have single shared instantiations, while others will be instantiated per slice. That will much depend on the specific objectives and the particularities of each deployment. Return now to the ITUR usage scenarios and key capabilities to elaborate a bit more on network slicing. In the middle left side, we can see a new figure showing how each key capability is seen by ITUT to impact each usage scenario group. We can see that enhanced mobile broadband is expected to be impacted by the largest number of key capabilities. Of course, impact will depend on service, but due to the large application spectrum expected in this area, it is understandable to be this way. Ultra-reliable and low-latency communications is very sensitive to delay and mobility. There is no identified key capability on reliability, but this is an additional aspect to take in consideration to support this type of services. For massive machine-type communications, large physical concentrations of these devices are expected. Thus, the 5G system must be able to support large connections density, which may lead to very noisy usage due to a large number of very small packets crossing the network and a very demanding control plane. Energy efficiency will also impact this, as IoT devices are expected to last several years without any battery recharge or replacement. This leads to an optimized control and data plane where, for instance, signaling related to mobility may be of lower importance. There is no KPI in coverage, as this is also very important for massive machine-type communications. This impacts the radio frequencies to be used to reach these devices and receive information from them. Current practice is to have the network providing the same service level to all applications. Thus, it is applications that adapt to the network behavior. And currently, we are only talking about internet applications. With the objective to cover the complete range of identified use cases, that has to change. As we'll have at least those three major group of applications, enhanced mobile broadband, massive machine-type communications, and ultra-reliable and low-latency communications, we may think about deploying 3 different physical infrastructures, each focusing in presenting the right characteristics to provide what is expected, for instance, low latency, high bit rates, high devices density, low power consumption, or high mobility. But that is not feasible due to cost and complexity. 5G addresses that with the concept of end-to-end network slicing. This means creating virtual networks on top of the same physical infrastructure. That will impact on the technology to be adopted to implement 5G, where SDN and NFV play an important role. As a reflect of the importance of this aspect, network slicing is the first issue identified in 3GPP Technical Report 23799. "5G New Radio is the new 3GPP access technology to be part of 5G systems. We will focus on it now. All previous generations came with a new radio interface. 5G will be no exception. As reflected in this statement from Qualcomm, this new radio interface is expected to be a unified air interface, meaning it shall be capable of being used by any device for any application willing to connect to a 5G core network. This represents a very demanding requirement. In fact, if we put together all the 5G requirements set by TUR and derived from use case analysis, the conclusion is that a new, very demanding radio access network is required. And as for the core network, slicing must now be applied to the radio interface. Thus, the new generation RAN must implement radio resources, mechanisms, and policies to support slicing. In the right side, we can see some of the technical aspects being addressed to answer the requirements on the left. These figures taken from CGPP Technical Specification 38300 show on the left the overall new generation RAN architecture, not so different from the 4G one. The new generation access network, or NG RAN, consists of GNBs and ENBs, so the new generation and the previous 4G generation node Bs. These last ones are not represented, but both are supposed to connect to core control and user plane functions located in the new generation core network. The figure on the top right summarizes the main functional split between the new generation node Bs and entities in the core network for both the control, where you can identify the AMF and SMF, and data plane. The QS architecture shows how packets shall be delivered and traverse the 5G core network. There will still be tunnelings and flows inside PDU sessions, so the similar concepts to the ones adopted in previous generations, namely 3G and 4G. Even if previous figures focus on 5G systems, there is a legacy network and several different options were identified for the interconnection of 5G components with legacy ones. One of those consists in using a 5G new radio with an APC core, which in what is called the non-standalone mode. With these, all the advantages of the new 5G new radio data plane can be exploited, still using a 4G control plane, what may foster 5G new radio deployments. As a reflect of the pressure and expectation around 5G, 3GPP at a recent WAN meeting had to add an intermediate milestone in order to have standard ready for the 5G new radio in March next year, with 5G new radio working in that non-standalone mode. Additionally, that work will focus on the feature required to support the enhanced mobile broadband use cases, what means higher bandwidth. Spectrum is an essential aspect of 5G wireless communications, as it was with 4G. Not only with only new higher frequencies, the envisaged bandwidth can be achieved. Currently, terrestrial wireless communications have allocated frequencies going from around 400 MHz to up more than 3 GHz. With 5G, it's expected to enter the millimeter wavelength, what means up to frequencies higher than 40 GHz. The drawback on this in going to so higher frequencies is that smaller cells will exist, requiring a much higher number of cell sites where those higher bandwidths will be required. The figure in the left summarizes a report issued by the European Radio Spectrum Policy Group, stating its position regarding a number of frequencies for 5G usage. We can see three different frequency ranges. Frequencies between 1 GHz required for macro cells and indoor coverage. Then we'll have frequencies that go till 6 GHz, the first to be used in 5G for more demanding use cases, with continuous spectrum of up to 400 MHz. And then we'll have frequencies that go above 6 GHz, up to more than 4 GHz, with the focus on 24 to 27 GHz to fully exploit the 5G potential and open the road for really very high bit rates. However, these high frequencies mean smaller cells, as already stated, and the signal not crossing all materials. Thus, its applicability may be limited to some hotspots with high commercial value, for instance, indoor hotspots in shopping malls. Thus, frequencies below 6 GHz shall be the preferred ones in the short term and medium term for 5G deployments. So what is the current status regarding 5G? So in order to provide you with a good perception of the current 5G development status, nothing better than presenting some of the most relevant, in my opinion, demonstrations already done. One of those was performed in November last year by SKT, Ericsson, and BMW, and it consisted in driving some cars at high speed along one track, exchanging several bidirectional high-definition video streams with the help of several 5G new radio antennas. Some gigabits per second were achieved, while beam tracking and beam transfer were in place, also providing, if not relevant for the demo, low latency communications. A very interesting video from the demo can be seen at the provided YouTube link. Some other demos were also run last year. I just identified a few here, focusing in different aspects. The first one, performed in Australia, shows the usage of higher frequencies to provide high bandwidth, in this case up to 5 gigabits per second at 4.5 gigahertz, and at the same time low latency. The second focused in carrier aggregation and massive MIMO. The third demonstrated the feasibility of real-time end-to-end network slicing crossing the RAN, core, and transport networks. Thus, we may say that all main 5G supporting technologies are emerging and, little by little, being put together. We may say that 5G is already becoming reality. Some final remarks regarding 5G. So we may say that there are very high expectations regarding 5G usefulness and impacts on all society and economic sectors. So the impact it will have in the society and economy will be very high, and that will start being a reality in 2020. Even though 5G is not technologically disruptive, evolving previous architecture and control principles, even is incorporating many new improvements. 5G standardization is on its way, with the target of having first 5G production networks around 2020, and there are several important global events that will foster this 5G development. In addition, we may say that some emerging complementary technologies like SDN, NFV, and MEC will have an important role in deployment and operation of 5G network. So, thank you for your time. Hope this presentation will be available for you and help you getting a first insight on the technologies. So as I said at the beginning, for any question you may have, please send me an email and I will be pleasure to answer to your questions. Thank you very much.